Use cylindrical shells to find the exact volume of the solid generated by rotating x equals 8y squared minus 2y cubed and x equals 0 about the x-axis. I've already graphed the curves below. If you're wondering how to graph these because they're solved for x not y, I would recommend Desmos. Using Desmos, you can simply type in the equations as given. Notice the bounded region is this region here, which we want to rotate about the x-axis. So again, this is the bounded region, or the bounded area. We want to rotate about the x-axis and then determine the volume of the solid. Whenever we're using the shell method to determine the volume of revolution, we want to sketch a representative rectangle that is parallel to the axis of rotation. Because we're rotating about the x-axis, we sketch a horizontal representative rectangle. It doesn't matter where it is. I'm going to go ahead and sketch it here. Notice the thickness of this rectangle is a change of y or delta y, which indicates we'll be integrating with respect to y, and therefore we'll be using this first formula for the volume of revolution when we have a horizontal axis of rotation, where the volume v equals 2 pi times the integral from c to d of r of y times h of y dy, where r of y is the radius function and h of y is the height function. And of course, the limits of integration will be y values. We can think of r of y as the distance from the center of the rectangle to the axis of rotation, this distance here. Because the axis of rotation is the x-axis, this vertical distance is simply y, giving us r of y equals y. And we can think of h of y as the height of the rectangle, which would be this horizontal distance here, which would be the x value from the outer curve minus the x value of the inner curve, which is simply 8y squared minus 2y cubed minus 0. So we know that h of y is 8y squared minus 2y cubed. And because we're integrating with respect to y, the limits of integration will be from y equals 0 to y equals 4. We'll also show how to find these algebraically in just a moment. Before we set this up, though, let's take a look at an animation. On the right, we see the graph of the bounded area. Let's rotate this about the x-axis. This shows the solid we want to find the volume of. And now let's go back and show a representative rectangle. So here we see a very thin representative rectangle. And now let's just rotate this rectangle about the x-axis. This gives us one shell, or one cylindrical shell, of the volume of the solid. And now let's show both the solid and the shell. Again, notice the shell is one slice, or one cylindrical shell of the volume. Going back to our work, we now know we'll be using the formula the volume v equals 2 pi times integral from c to d of r of y times h of y dy, where we already know that r of y is equal to y and h of y equals 8y squared minus 2y cubed. We can also tell from the graph the limits of integration will be from 0 to 4, which indicates c equals 0 and d equals 4. But just in case we weren't able to determine these exact values from the graph, we would solve the two equations given as a system of equations. Because they're both solved for x, we could use the method of substitution. Substituting 0 for x in the first equation, we can determine the limits of integration by solving the equation 0 equals 8y squared minus 2y cubed, solving by factoring. Factoring out 2y squared, we have 2y squared times the quantity 4 minus y. The product on the right is equal to 0 when y equals 0, or when 4 minus y equals 0, giving us y equals 0 or y equals 4, which are the limits of integration. So putting all the pieces together, in our case, the volume v is equal to 2 pi times the integral from 0 to 4 of r of y, which is y, times h of y, which is 8y squared minus 2y cubed dy. Before we determine the antiderivative, let's distribute the y, which gives us the volume V is equal to 2 pi times the integral from 0 to 4 of 8y cubed minus 2y to the fourth dy. And now we determine the antiderivative. And don't forget about the 2 pi. We have 8 times y to the fourth divided by 4 minus 2 times y to the fifth divided by 5. Let's go ahead and simplify the antiderivative. We have 2y to the fourth minus 2/5 y to the fifth. And now we determine 2 pi times the difference of big F of 4 and big F of 0. Big F of 4 is equal to 2 times 4 to the fourth minus 2/5 4 to the fifth. And then, of course, big F of 0 is simply 0. Simplifying, we have 2 pi times the difference of 512 and 2048 divided by 5, which is 2 pi times 512 divided by 5, which is 1024 divided by 5 pi. And because this is volume, we can say these would be cubic units. I hope you found this helpful.